Have you ever seen a fraction like this and wondered how exactly you're going to divide this fraction by a seemingly random number to get suddenly 9 over 10 with just a couple operations? Well, if you want to know how to get that quote and unquote random placeholder, then this is the video for you guys. Hi guys, welcome back to LIC, and today we're going to talk about GCFs and prime factorizations. Okay, the first thing you have to tackle is the concept of simplifying. Basically, simplifying is the act of changing the numerical values of a fraction into smaller parts without changing the actual value of the fraction. To show this, let's take this square, okay, and divide it equally into 2 as seen here in the second picture. If we shade one side of this, we can all agree that this shaded region is taking up 1/2 of the square, right? However, what if we add another line horizontally that cuts this suddenly into 4? If you look closely, even if it's cut into 4 now, it's 2 over 4, right? We can still see that this covers the same amount of space as the 1 over 2 here, or the 1/2 here. This is because some fractions have the same values as others, even if they have different numerical placeholders. If you didn't catch that, basically it just means that relative to the whole, some factors will take up the same proportions as other factors with different numbers will. You may be wondering, however, how can we get the bigger fractions into becoming smaller fractions that are worth the exact same? The way we do this is by finding something known as the GCF. Now, what's important to talk about before we discuss the GCF is that we have these things called factors in math. Factors are basically just numbers that when multiplied together lead to the original number. For instance, if you multiply 3 times 4, you're gonna get 12. This means that 3 over 4 are both factors of 12. Okay, catch that? It's basically just simple recap. Okay, ending that recap, the GCF is actually an acronym for the greatest common factor, which means that it's the highest number and you can divide both the numerator and denominator by to get to the simplified version. It is very important that the number you divide for the denominator and the numerator is the exact same, as otherwise you could change the value of the fraction by making one higher than it's supposed to be due to the operation values not being the exact same. Okay, now that we got the meanings behind the words out of the way, we have to start trying to find that number, that GCF we divide fractions by. There are multiple ways to do this, but to make it a bit easier, we'll discuss those ways using numbers and example. For this example, let's use the fraction 12 over 18, okay? The first method you can use to find the GCF is known as the listing method. As it says in the name, the listing method is the act of listing all the factors of the numbers and comparing and looking at the biggest number shared between both of them. So in this case, the factors of 12, let's list them down, can be 1 multiplied by 12, 2 and 6, and 3 and 4. Pretty simple, right? Okay, let's do the same thing for 18. Here we can see that in 18, we're going to have 1 and 18, 2 times 9, and 3 times 6. I'll give you guys a minute to process that and to look for the GCF between them. Looking back into it now, we can see that 6 is the greatest common factor between them. So you can divide both the numbers in the fraction, which are 12 by 18, by 6 for the 12 and 6 for the 18, right? The greatest common factor. And this simply simplifies it into 2 over 3. Okay, catch that? Moving on to method 2, which is the harder method, we have prime factorization. Now before we get into it, we have to talk about something known as prime numbers. Prime numbers are numbers that cannot be divided or do not have any factors aside from one of themselves. Examples of these are 2 and 3, 5 and 7, and so on and so forth, etc. Now, because these things cannot be divided and made smaller. They have a very interesting role to play, mainly in this method we will discuss now. You see, the problem with listing is that you list down pairs of numbers that when multiplied together make the original number. This is all well and good until you get to the bigger numbers like, let's say, 64. In this case, you'll need to write down 1 times 64, 2 times 32, 4 times 16, and so on and so forth, right? This problem will simply get worse and worse as you get to the bigger numbers in the hundreds, even thousands, right? Meaning, it'll become harder to find the GCF through listing, which is where this second method comes in. You see, the cool thing about big non-prime numbers is that they're made up of little prime numbers multiplied by each other. The reason is because prime numbers are the only numbers that cannot be made into smaller factors, because its only factors are 1 multiplied by itself, which means that every other number that is not a prime can be reduced and reduced and reduced and reduced until you get your prime factors. So prime factorization takes a big number and breaks it down into all of its teenier prime factors, allowing you to have a set of numbers that when consecutively multiplied gives you your original number. That means you don't have to multiply things in pairs. You can just take all your prime factors all at once and multiply them all together. The good thing about this method now is that you can directly compare all the similar prime factors of your numerator and denominator, then multiply the common ones to get your GCF. That's a lot of word vomit, so let me just show you what I mean with an actual example. Let's take the same problem from earlier, which is 12 over 18, right? And let's use prime factorization this time. If we break down 12 into its prime factors, we're gonna get 2 times 6. Actually, no. But we can see here that 6 can be broken down even more. So we're gonna get 2, and then 6 can be broken down into 2 times 3. So we're gonna get 2 times 2 times 3. Let me put that here. 2 times 2 times 3. Same thing for 18. We're gonna get 2 times 9. But we know that 9 is 3 squared, which means that 9 can be broken down into 3 and 3. So that gives us 2, 3 times 3. Get it? Okay. Looking at these numbers, we can see that we have 1 2 in common and 1 3 in common. Right? If we multiply those 2 and 3's together, we will... My bad. If we multiply 2 and 3 together, we will get 6. Right? And 6 is our GCF for this given problem. Which means that if you divide 12 and 18, divided by 6 and 6 for each of them, we will come back to the answer from earlier, which is 2 over 3. Another thing you can do though, if you have already noticed, is that you can just cancel out the common factors and get straight to the last or smallest numbers, in short. So if you wish to do that, feel free to do so. So let's just try that out here. You're gonna cancel out this 2 with this 2, and this 3 with this 3. That leaves us again with 2 over 3. So it doesn't matter actually which method, for this problem at least, you would prefer. However, do note that when you get to the bigger numbers, it will be harder to list them down. So I think it's still good to know, or at least take note of this method. And for the smaller ones, however, just feel free to do whatever you're the most comfortable with. And yeah. Oh, another thing of importance though is that, let's use 12 over 18 again. You have to multiply or divide these, I guess. You have to divide these by the same numerator and denominator, because if you look at it, 6 over 6 essentially is actually just 1, right? And we know that any number you divide by 1 will be the exact same. Why we want to do this is that fractions have the same value, it's just that they're named differently, right? what we want to do here is to bring out the smallest of smallest values, which without actually changing it. If we do change it, let's say we divide 12 over 18 by 3 and 9, right? Or 3 over 6, so that's closer. We'll suddenly get such a different problem that it's not even the same fraction anymore, which is something we do not want. So if we divide it by 3 over 6 instead of 6 over 6, which is equal to 1, we'll suddenly get 4 over 3, which is not the same as 2 over 3 and is not the same as 12 over 18. So just keep in mind that when dividing it by the GCF, it has to be the same digits. I mean, the same number. Okay? Well, that's it for today on GCF and Prime Factorization. Please feel free to comment on topics you want to be discussed. May they be purely out of your own interest or because you have an upcoming test this week and you need to learn it ASAP. Okay? Thank you for tuning in to LIC and we'll see you next time. Bye.